Hey everyone, welcome back, and today let's solve Leetcode problem 3191 titled Minimum Operations to Make Binary Array Elements Equal to 1 Part 1. So on a high-level rundown, what this problem is really telling us is that we're given a binary array nums. It's going to consist only of zeros and ones. That's kind of how a binary array is defined to be. And our goal is to determine the minimum number of operations required to transform all of these elements in the input array to only ones. And the only allowed operation that we can do is to select any three consecutive elements or window of three elements that are of course consecutive in the input array and flip all of them. And what they really mean by flipping them would be changing a 0 to a 1 and a 1 to a 0. However, if it's impossible to achieve an array of all ones, we have to return -1. So let's go ahead and look at how the examples kind of depict this. In example 1, we have our input array nums to be 0, 1, 1, 1, 0, 0. Notice how we have 3 ones and 3 zeros. Our goal is to have all 6 ones, meaning we want all the elements in the input array to be ones. In this case, the reason why our output is 3 is because that is the minimum number of operations of selecting 3 consecutive elements at a time and changing them, or rather flipping all of them to be zeros and ones to zeros. And the way that would work is we could first select the elements at indices 0, 1, and 2, meaning the very first 3 elements of the input array. If we flip them, we'd get 1, 0, 0, 1, 0, 0. Then we can choose the next set, or 1 shifted to the right kind of trio of indices. So instead of 0, 1, and 2, now we could take 1, 2, and 3 at those specific indices and flip them. Then we get 1, 1, 1, 0, 0, 0. And notice how the pattern works. Once we get that, we really only have to flip these last 3 eventual zeros at indices 3, 4, and 5 and flip them all to be ones. And so we get 1, 1, 1, 1, 1, 1, and we finished the problem's requirements in just 3 operations, which is the minimum number that we could have taken, and so that is why we have that specific output. Notice how we started off with these initial indices, and we worked our way towards the end of the array, flipping all of the zeros to make them ones if needed. In example 2, we have our input array nums to be 0, 1, 1, 1, and in this case, it's actually completely impossible to make all of the elements equal to 1. We could change this to 0, or rather, we could change the 0 to a 1, and then these two to zeros, and try with these 3 elements, but regardless of what we do, we're not going to have all 4 of these elements equal to 1s. The most we can have is 3 at one time. So that's why we have an output of -1. So for the constraints of this problem here, we see that the length of the input array is obviously going to have at least 3 elements to even choose, and going to be a maximum of 10 to the 5th power, where any value is either going to be 0 or 1. So we're guaranteed that the array is going to be an input binary array, and we're not going to have any invalid inputs with other different elements or integers, right? So that leads us to the main observations that we can really make for the context of this problem to really solve it. And that is kind of like how we saw in the initial example where we worked our way towards the end of the array starting from the beginning. Whenever we actually encounter a 0 in the array, as we actually iterate through the array, we know that it must be flipped to a 1 to actually achieve our goal. There's no other way of actually achieving our goal. We have to flip that 0 that we're currently at to a 1. And so to do this in the most efficient way possible while minimizing the number of operations that we can make to actually fulfill the problem's requirements, again, like I was talking about, we're going to traverse the array from the beginning, not till the end, because we don't want to have an index out of bounds or go to out of bounds, right? We want to go to the third to last element, right? Because we're gonna be changing and comparing the last 3 elements or every single consecutive 3 elements, and so we can't actually be on the second to last or last element, because then we'd have out of bounds error. So we're going to go through the array from the beginning to the third to last element, and each time we actually encounter a 0 at any position or index I, we'd have to perform or simulate that flipping operation on the elements at indices I plus 1, and I plus 2. Basically, the current index and the next 2 elements that are adjacent to it to the right, that come directly after it. And then, of course, once we actually apply that flipping operation on those 3 elements every time we encounter a 0, we have to then, of course, increment the operation count, right? That's going to actually keep track of how many operations we made in the input array. And after we've completely finished traversing the input array, we check the last 2 elements. If either one of those last 2 elements was a 0, we know it would be impossible to convert the entire array to 1s using these allowed operations of flipping only 3 elements, and so we have to have an output of -1. However, if the last 2 elements are not 0, they're both 1s, we know we have fulfilled the problem's constraints, and we know that we would be able to actually change all the elements in the input array to be ones, because we're guaranteed that by the end of traversing the array, all the elements from the beginning up until the third to last element are going to be ones, because we make sure of that when we iterate through them. As long as the last two elements, the elements that are not in our control, the elements that we cannot change, as long as they're also ones, we know that we can actually change all of the elements to ones. And otherwise, in that case, we simply return the total count of operations performed if we did actually pass the constraints, where both the last two elements are also ones as well, like all the other elements as well. So let's go ahead and get into the code here. So what I'm going to initially do is actually initialize my answer. And like we talked about, this is really just the main output. This is going to actually keep track of the number of flip operations we made on the input array, eventually what we're going to return. So I can actually have that out right now if I really need to. So now let's actually begin the processing or iteration of the array. And so we're going to go up until the third to last element to avoid getting an exceeding input array index out of bounds. So when we're actually accessing the i+1 and i+2 indices, so for I in the range of the length of the input array nums -2, right, because we don't want to go to the last two elements to go an index out of bounds, we're going to first check, okay, is the current element, does it need to be flipped? Meaning, is the current element nums at index I, is it a 0? If it's a 0, it's bad. It's kind of like a bad character, and we want to flip it. We want to flip it, and of course, we have to flip the next two elements as well, because that's how the operation is defined to be. So if it is a 0, we have to actually apply the operation. And a neat way to do that in Python here is actually use something like called the bitwise manipulation operation, more specifically the XOR operation, really just a flipping operation from 0 to 1 and 1 to 0, and nothing much to worry about there. So if the current element is 0, we want to change this element, and we also want to change the next two elements to then be 1s, right? So we're going to go rather be bit flipped by 1. Just flip them, right? So we'll get nums at i+1, and bit flip it by 1, or rather just bit flip it in general, and nums at i+2, and bit flip that as well. And what I really mean by bit flip is this is, again, the XOR operation. So if nums at i+1 was a 0 originally, it'd go to a 1. If it was a 1 originally, it'd go to a 0. We're really just changing the bit of this of the elements at these next two indices to either be a 0 to a 1 or a 1 to a 0, right? If the current element is actually 0, we know we have to actually flip the element at index i+1 and i+2 using that XOR operation, right? Kind of applying the operation that they gave us. And that kind of symbolizes that we've used one more operation, and so for that reason, we have to increment the number of operations we did by 1 as well. It could change this to operations, but I hope you guys understand the kind of use case of this answer variable, right? Now, once we actually get out of this for loop here, once we've iterated through all the elements, great. We're guaranteed that all the elements from 0 up until the third to last index or element, they're all going to be 1s because we changed them as we actually iterated through the array. But the only two elements that weren't in our control would be the second to last and the last element, because we didn't actually iterate over them, and we didn't check if those were 1s because we want to get an index out of bounds, and so we didn't convert them to be 1s either. So we're going to return -1. That's only if nums at -1 is 0, meaning we didn't actually successfully make that a 1, or nums at -2 is 0. And in Python, what -1 and -2 indices really mean, basically they're the last and second to last indices. If either one of those things are 0, we know that we couldn't actually successfully, or rather it's impossible to convert the entire array to 1s if the last or second to last element is 0, and so we're going to return -1. However, if that's not the case, so else, we're going to return the number of operations that we made, right? The total number of operations that we performed in the input array, and where is that stored? Well, it's stored in the integer answer. So in fact, I don't even need this return answer because I had this nested conditional right here. So that's all we really need, right? So unless I made any syntax errors here, this should be accepted, and this should be a valid solution. Let's go ahead and double check that. And as you can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, the way this solution really works, effectively we're just iterating through the binary array nums. It's a one-pass solution, and each time we actually encounter a 0, we have to then flip the next two elements, kind of simulating performing that operation. And we're always ensuring that the current 0 is always turned to a 1, and so by the end of the iteration, we know we're guaranteed that all the elements from the 0th indices, basically from the beginning of the input array up until the third to last index, are going to be 1s. And so if the last two elements are both 1s, we know that the entire array has actually been successfully converted to all 1s, and so we simply return the total number of flip operations that we performed. However, if either of the last two elements are still 0, we didn't fulfill the problem's requirements. And that also indicates that it's impossible to convert the entire input array to all 1s using that allowed operation of 3 consecutive elements and flipping them, and so we have to return -1. right? So for the runtime complexity of this solution, it's actually going to be, again, linear, big O of n, and it's going to be the length of the input array nums. Why? Because, again, it's really just a one-pass solution, a single iteration, single for loop solution here. We're just iterating through or traversing the array exactly once, and we're, of course, performing some constant time operations during each iteration, but that's not going to affect our runtime complexity, and so this really is just a big O of n operation where we basically hit all the elements except for the second to last and last one exactly once. And for the memory or space complexity, believe it or not, it's actually going to be a big O of 1 or constant time runtime, because of course the algorithm does actually modify the input array in place. We're not using any auxiliary memories or any extra data structures, only using a fixed amount of additional space for these integer variables like answer. And so that's going to be a constant time memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.